And if someone would be kind enough to work that out, preferably more than one person.
I got 1.99 10 to the 30th.
I got that.
All right. You said you got that also?
Kilograms.
And I think that actually is what's in the book. Oh, they had 1.9891. All right, so mass of the sun. So we don't need to collide anything into it in order to do experiments that way. We could also find the mass of the Earth based upon the orbit of the moon around, and so on. Now, questions up to here?
Just a curiosity. I remember that Einstein was baffled that Mercury didn't obey, was not really predicted by the Newton things.
Right.
And he was using this formula for calculating the Mercury radius or not?
I assume, because he was, I mean, you're just dealing with, that's pretty much all they had. You had this until general relativity comes along. So that's my understanding of it. And what Roberta is talking about is that planets travel in an ellipse. They don't actually travel in a circle. So first, one thing about if we're actually dealing with an ellipse, flashback to whatever course you do conic sections in. Is that pre-calculus? Trig? Okay. That's supposed to be an ellipse. And you got two foci. The sun is at one of the foci. And the planet travels in an ellipse. So in an ellipse, you have a major and minor axis. The major axis is the longer one, the minor axis is the shorter one. And the distance from here to here is basically the length of what's called the semi-major axis. Typically, every time I've seen it, it's been symbolized by the letter A. And so the only difference is that if you do it the long way, this becomes A. So if you do go through the formality of it.
So an ellipse has the same circumference as a circle?
Say it again?
An ellipse has the same circumference as a circle?
No, I don't think it does. But if you go through the Picayune aspect of it, this is what it comes out to be. Although I've done it with just the average orbital radius, and it still comes out pretty close for most of the planets. I expected Pluto, since it's got the most eccentric orbit, to be the farthest out, but Pluto actually works pretty well too, just with average. And yes, Pluto's a planet till I die. Maybe it's why the astrophysicists wouldn't invite me to anything. Now, so for the most part, the Earth if we consider the sun not moving, most of the planets do sort of travel around and they basically follow the same relative path. Mercury, not that extreme, but Mercury gets a little bit off, like a spirograph. Cultural reference from my childhood, and spirographs, they still around? I got one nod over there. Okay. So it's a little bit off, and this cannot predict that. General relativity gets closer. That's my understanding of it. My general relativity is weak. Is that?
No, I think he got it
Okay.
pretty good.
Suddenly I had flashbacks to my general relativity class. All right. Am I done with 7? Gravitational field. I don't do much with that. Kepler. Oh, do I subject you to it or not? I am going to subject you to it. All right. Any questions? We're about to go through just an absolutely spectacular derivation. Just because I want to see you sort of blend the calculus in with this, since you've had calculus here.
Wait, so it's the same derivation? Or a different one?
A different derivation. Yeah, if I were doing the same derivation, that's one that I did it this year, and I actually videoed it this year. I did it about 6 or 7 years ago in my notes, and then I did it when I was in graduate school. It's not one that I could easily do cold. However, the next one I can't do incredibly cold, so I do need my notes for it. All right, so what we're going to do is we're going to take a thin-shelled sphere. So we have mass all along this outer border here, and it's basically empty. It's a hollow planet. And what I want to know is, so we have centered right here, I want to take some point inside here. What is the gravitational pull? What's the force due to gravity at this point inside the sphere? First, let's just take the really easy one, the conceptual one. What is the gravitational pull at the very center of this sphere?
Zero.
Right. Why?
Because it's your path origin. And that's where it's pulling you, that's where it wants you to end up at, I guess.
Let's see if we can flesh out that why.
There's like nothing to pull you any closer?
No.
I guess that's the origin of the force.
No, the origin of the force is the mass right here sitting on the side here. All right, so if I have a mass here and a mass here, what's the direction of the gravitational pull? Okay. So if I'm at the very center of this sphere, well, this is pulling me that way, but there's also something over here pulling me that way. I have something pulling me this way and that way and this way and that way and this way and that way. For every place, for any point that's pulling on me, there's something on the opposite end of the other side of the sphere also pulling me in the opposite direction. So that's why the total, I'm not saying no forces are acting on me, I'm saying the total force is 0. So you would definitely be in equilibrium at the center in our nice ideal situation here. All right, we need to define some points. What I'm going to do is I want to create an axis that basically goes through that point. I guess indicate inside and outside. That is supposed to represent sort of an X, Y, and Z axes. So we'll just call that one X, that one Y, and that one Z. I think it's going to end up throwing me, so I'm just going to reorient this. I'm going to take this and just turn it and make a lesser circle. So my X-axis, Y-axis, and then Z is coming right out at us. It's the same thing, I've just reoriented. So I have some point here, which I'm going to call point P. The center, I'm going to call point C. There is what color is that going to get? And I apologize, I'm going to move this over to this side. I think if I leave it there, it's going to get, the picture's going to get really cluttered, and it's going to be bad enough as it is. So I'm going to put P there just so that this next bit, just a little bit easier. All right, so I have this distance from my point P to this ring along my surface. So we have our hollow sphere here, we have something inside, and everything along this ring here is equidistant from this point. So the distance from this point to any point on this ring is the same distance, which we're going to label as S. The radius of the sphere is R. There's an angle right here of theta. That's the center. And this angle right here, I believe alpha is what I've done before, yeah, alpha. So what we're trying to find is the gravitational pull at point P. Now, this ring right here has a particular mass, but this is an infinitesimally small ring, and so it has a mass of, we'll just call dm. The mass here we'll just call mass 1. So the gravitational pull, well, we can come up with a differential for the gravitational pull. Since it's a gravitational pull between a mass and an infinitesimally thin ring, in other words, an infinitesimally small mass, this would just be big G times mass 1 dm over s squared times cosine alpha I hat plus sine alpha j hat. Because they're components, we're dealing with vectors here. Oh, which you wouldn't guess from the notation I just used. There we go. So we're doing an integral. Now, one of the reasons for putting our point P on an axis is the next step. Now in math class, you can actually go through this part of the derivation on your own, but in physics, we get away with thinking through it. Thinking about just this ring right here and this point. What is the direction of the net force on this point from that ring? Why not vertical?
Each one will cancel because one goes like that and the other like that.
Because for every force that's trying to pull it up, there's one trying to pull it down. So ultimately, if we work through the math here, I guess technically then F is equal to G M1 dm over S squared cosine alpha I hat plus G mass 1 dm over S squared sine alpha j hat, just distributing. And this is 0. Just by the fact of the symmetry of the situation, we don't have to do the math, we know it has to be 0. But if you're not convinced, you can work through the math and you get 0. So we've already gotten rid of half our problem, right there. So my force is equal to G mass 1 over I hat times the integral of dm over S squared cosine alpha I hat. Oh, wait, what do you have for I hat? So I just pulled the constants out. I didn't officially define I hat, so let's go ahead and define I hat, J hat, K hat. And again, symmetry argument for getting rid of all the z components. The trouble is, I have an integral here, and I'm assuming at this point you've done basic integrals. Okay. The integrals here, I've got 3 variables. So we need to somehow get it down to 1 variable to make it doable. So let's start with dm. Before I do that. And in terms of my notes, did I use sigma for this one? Yeah, I use sigma. Okay. Sigma is known as the surface density. Since it's infinitesimally thin, and if we wanted to give it thickness, then we would not be using sigma. So first off, what is density? Flashback to chemistry or at some point in your life. What is the formula for density?
Mass over volume.
All right. What is the formula for surface density?
Mass of the surface over the volume. Surface.
Mass over, not surface volume.
Area.
Yeah, surface area. It's mass over area. So sigma would be, if we're talking about differentials, dm dA. And so therefore dm is just sigma times dA. Great, we traded 1 variable for a different one. No, this actually will help us. So if I think about this ring that we have here, the area of this ring. If we do a zoom in on it, everything has some incredibly infinitesimally small width here. This right here is this section right there. This is the radius of the sphere. Actually, do I want it in terms of theta? Yes, I do want it in terms of theta. So the thickness of this angle here is some differential of theta. Just because theta is the angle from here to here, and we're just talking about this tiny little wedge right there where I've drawn my red line.
Sorry, which one are we zooming into again?
We're zooming in on this right here. So if I have a radius of r and an angle of d theta, what is the thickness right here?
R over
R.
d theta.
Say it again?
R over d theta.
Ooh, no.
Not R D theta, the same.
It's r d theta, not over. That's just r d theta. The whole arc length is equal to the radius times the angle. So my radius is big R, the distance from there to there, and theta is d theta, so r d theta. So that's the thickness of this little band right here, but I'm trying to find the total surface area because that's just a one-dimensional, that's just one-dimensional here. So I have this ring here, and I basically, if I pulled that ring off and I cut it and stretched it out, well, there's the thickness of this really thin ring, and the length is just the circumference of this circle right here. And the circumference, as we discussed earlier, 2 pi r. So my area, sigma times r d theta, times however long this ring is, 2 pi times, well, radius of the hoop. Keep trading one variable for another one. It does all settle out in the end. The radius of that hoop, and again, just want to make sure that I'm doing it all in terms of theta here. I know that this black line right here is the radius of the circle itself, of the sphere, and so that's r. I have this angle theta here, and so this, if we look at just that triangle, so r theta, this would be r sine of theta. So that would be the radius of the hoop. And so this becomes sigma r d theta, 2 pi r sine theta. And so this now becomes g mass 1 I hat integral of, this is all dm, sigma r squared 2 pi sine theta d theta over s squared cosine alpha. Let's make sure I didn't lose something there. So I got my 2 pi still, I got got my r squared, got my sigma, and then sine theta d theta. This up here, this is all constant. I can just pull that right out. So g mass 1 sigma r squared 2 pi I hat sine theta d theta over s squared cosine alpha. See how much simpler that is? And we still have 3 variables. So let's get rid of some of them. If I label this point as point Q, I want to look at the triangle CPQ. So I've got this little stretch right here. This is point P. This is point C. This is point Q. I know this angle here is theta. This angle here is alpha. That is S. And let's make sure I'm using the right, what am I using for that one? Yeah. And this distance right here, we're just gonna make R, little r. And that length right there is capital R. Right. Take a moment just to convince yourself that, what that triangle is representing. Let's see if I can highlight it without losing stuff. Looking at this triangle right here. Questions up to here? All right, law of cosines. What does S squared equal?
Square root R squared plus R squared.
No, it's just R squared, little R squared plus capital R squared, I guess.
Were you stopping there?
No, you said capital R squared.
Okay, I got it.
Take the square root.
Oh, not there yet.
You wouldn't take the square root because S is squared.
That this is not a correct statement. This is Pythagorean theorem, which only works if it's a right triangle. It's not a right triangle. Law of cosines. Flashback to
Sine A, no, A over sine A is equal to,
law of sines. It's the other one.
A over cosine A is equal to B over cosine.
That would have been really nice if that had worked. No.
Should got it.
It's basically, it's like Pythagorean theorem is a special case of law of cosines. Minus 2 little r big R cosine of whatever the angle is opposite of S, which is this one right here. Yeah. Cosine of pi minus theta. Just a quick side note over here, law of cosines. If this is alpha, beta, gamma, A, B, and C, A squared equals B squared plus C squared minus 2BC cosine of alpha, law of cosines. Now, ultimately, we're trying to get cosine of alpha here, so, well, we have a formula which isn't really cosine of alpha yet, so we need to somehow get it there. Cosine of pi minus theta, what does that simplify into? Again, flashback to trig.
Oh, it would be, I don't know what it's called.
You're trying to think of the formula, or you're trying to think of a different word?
Not a formula, no.
Okay.
I'm just forgetting.
Cosine of, we'll put this over on the side over here. Cosine of alpha plus beta is cosine of alpha cosine of beta minus sine alpha sine beta. Take a quick moment just to make sure this is right. So if Yep, feeling good. So cosine of alpha minus beta is cosine alpha, cosine beta, plus sine alpha, sine beta. So if we're dealing with pi and theta there, just this piece right here becomes cosine of pi, cosine of theta, plus sine of pi, sine of theta. What's cosine of pi? Yep. Sine of pi? So that whole side drops out. And what we're now left with is s squared equals little r squared plus big R squared plus 2 little r big R sine of theta. So we're actually solving for sine of theta now, not cosine alpha, as I mistakenly said earlier. Sine of theta, therefore, is s squared minus little r squared minus big R squared divided by 2 little r big R. Just double checking, make sure I didn't go astray somewhere. Oh, wait.
How do we get this?
Yeah. I assume that's what you're about to point out?
Yes.
Okay. Oops. It's probably not my last mistake. All right. So we have this cosine of theta here. How do we get sine of theta if I know cosine of theta? If you have cosine, how can you get sine?
Take an integral.
Okay, yeah, or the other way. Yeah, that's gonna be a little bit simpler. So this becomes 2s ds is equal to, well, that's the distance from the center to wherever my point is, so that's actually a constant. So that's 0. That's the radius of the circle or the sphere, that's a constant.